Right, so today we'll continue looking at section 6.3. We'll finish up the last two transformations that we're going to do individually, which are your vertical stretches and horizontal stretches, or compression. And then tomorrow we'll still look at sine and cosine, but we're going to start combining multiple transformations in the same problem, and that's when the order becomes important. So the first transformation we're going to look at is the vertical stretch or compression. So when you stretch or compress something vertically, okay, what we're going to be doing is affecting what's called the height or the amplitude. And I have a picture here showing you what the amplitude is. And it's the distance from the center of the wave to the highest point. All right, so the amplitude basically, it measures a distance or it measures a height. So if a number measures distance, what kind of number does it always have to be? Yeah. Positive. Yeah, it always has to be positive. Okay, there's no such thing as a negative amplitude. What's the amplitude of the sine and cosine function normally, if you don't do anything to it? Yeah. 1. Okay, the amplitude is 1, which is also happens to be the highest y value it ever hits. But those two questions aren't always the same answer. Because if you had a graph like this, that's still an amplitude of 1. Right? Because if you put the center line in, the highest it goes off the center line is 1 unit. But the highest value in the range that it hits is 3 in that case. Okay, so you have to keep in mind the difference between the highest value and the amplitude. Sometimes they're the same, sometimes they're different. Okay, so both stretches that we look at today, stretches always involve multiplying. Where you multiply controls whether it's horizontal or vertical. If you multiply outside the function, that's a vertical stretch. And why do you think I used the letter C? Yeah?
Well, I remember the other day you said A, B, C, D, and like A was phase shift.
Yep.
They went in order,
Yep.
a certain order, so that's the third one.
Yeah, this would be the third transformation. If you had a problem with every transformation in it, this would be the third thing you do. Right. So, regardless of what the number is in front, whether C is a positive number or a negative number, if I ask you for the amplitude, you have to make sure you give me the absolute value of the number in front. Right, I think, let me see if I have an example. Yeah, I've got some examples we'll look at in a second. Okay, so changing the amplitude is going to stretch or compress the graph along the y-axis. And it's always nice when the y values change because those are the easy ones. Right? When the x's change, then you've got to work with fractions that have pi. But for this transformation, you get to work with the easy column. All right, so one type of question I'm going to ask you on the test has nothing to do with graphing. It's just going to be looking at an equation and identifying the amplitude. That's all you're going to have to do. So let's try that. Okay, so example 1 says find the amplitude. So let's start with 3 cosine x. Leo, what's the amplitude there? 3. Yep. All right. The next one is 4/3 sine of x plus pi over 2 plus 6. What's the amplitude there? 4/3. Okay, there's a couple other things going on there that we talked about yesterday. There's a phase shift and a vertical shift. But that has nothing to do with the amplitude. How about -2 sine x? What's the amplitude there, Rebecca? 2. Yep. Now what if I change the problem to that? What's the amplitude now? Still 2. So the negative has no effect on the amplitude, but it does have an effect on the graph. What does a negative cause the graph to do? Yeah?
Reflect over the y-axis.
It's a vertical reflection. So I agree it is a reflection, but it's going to be over the x-axis because it'll be up to down, vertical. So like if you had something like this, it would end up down there. So the negative, all that would do is if you had a graph like that, it would make it like that. So it doesn't change the height of the graph at all. It just flips it over. Okay. So it's important when you graph, you take into account the negative. But when you tell me the amplitude, you get rid of it. Okay, that's the only time you get rid of it is if I ask that question. Find the amplitude. Okay, so just like phase shift and vertical shift, we got to figure out where the 5 points from the original table are going to go. Since we are stretching and compressing along the y-axis, the x column stays the same. Okay, so until we do multiple transformations tomorrow, the x's for a vertical stretch are always going to be 0, pi over 2, pi, 3 pi over 2, 2 pi. So copy those from the original table. Okay, the y's, to find the new y values, all we've got to do is multiply the old y values by c. Now, notice there, I didn't say absolute value of c. You can just take whatever the number is in front, positive or negative, and use it the way it is. Because the negative definitely has an effect on the graph. Just not the amplitude. Okay, so for this transformation, arithmetic, super easy. Okay, because you're just going to multiply a 1, a 0, or a -1 by a number. Okay, so we'll do an example of a vertical stretch, and then we'll play a sound, and you can see what that would sound like. Okay, so 3 cosine x. So sometimes when we do transformations, they do the opposite of what you would expect. Sometimes they don't. Okay, with phase shift, we learned that it's the opposite of what you would expect. With vertical shift, it's not. How about vertical stretch? Do you think this is going to stretch it 3 times taller or make it 1/3 as tall? Let me guess what's going to happen here. How about, yep, Leo?
Times larger.
3 times larger, yeah. It is going to stretch it 3 times as much. Vertical transformations always do what you would expect. It's the horizontal ones that do the opposite. All right, so we're stretching it along the y-axis. So Jayan, what are my x's going to be?
It'd be 0 over 2, pi, 3 pi over 2, 2 pi.
2 pi. Okay, so I've got all my x's. Okay, so just like I said yesterday, you get 1 point for each x value you get right. So that's 5 points. And now the y's. Megan, can you give me my original y's for cosine?
For sine?
Cosine.
1, 0, -1, 0, 1.
And now, Abby, we're going to take all those values and multiply them by
3.
3. So we're going to get 3, 0, -3, 0, 3. 5 points for those y values. Okay, any questions on that? Okay, now we're going to make our sketch. This time, I'm going to scale my axis from 3 to -3. You don't have to scale it that way, but This is how I did it. And then along the x-axis, put in your labels. Pi over 2, pi, 3 pi over 2, 2 pi, I've got an extra one I don't need. And now just graph it. So 0, 3, 0, negative 3, 0, back to 3. Questions on the graph? Just try to make it look curved again. It shouldn't have points on it. Okay, don't make it like a V. All right. Now, that graph looks pretty much the same as the kind of graphs we did yesterday with cosine. How come that graph doesn't really look different? It's something I did that's going to make it look the same. Yeah?
Because you set the y scale to just 3, negative 3.
Yeah, I changed my scale. Right? So if I wanted to graph 7 cosine x, I would graph exactly the same picture and change the numbers. So all my pictures for cosine are going to look the same today. All of them for sine are going to look the same. But I'm going to change the scale. Okay. So any questions on that? All right. So that's a vertical stretch, and it did get 3 times as tall. Okay. If you were to imagine the original, it would be, let's see if I can make a copy of this and just try to compress it on one axis. Well, it's kind of hard to make it accurate, but it would be something kind of like that. It would be between -1 and 1. All right, any thoughts about what that would sound like if you compared a sound wave like that to a sound wave like that? Thoughts? Yeah?
Would it have a higher pitch?
Okay, so it could change the pitch. What else can we change about the sound besides the pitch? Yep.
Volume.
The volumes. It's going to be one of those two. This one is actually the volume. So let me, okay, so let's take a look. So here we've got our program where I can generate the different tones. Okay, so let me make sure it's not super loud. Just give me a second. Okay, so that's 1,000 hertz tone. If I lock the left and right together so they're changing at the same time, because I don't want to have one speaker louder than the other. And I play that sound. Okay, got much softer. And then if I play that, it gets much louder. So stretching and compressing vertically with a sound wave has to do with the intensity of the sound. And with a sound wave, intensity is volume. That's how you hear it. Other kinds of waves, which we don't really talk about, are electromagnetic waves. Those are waves like radio waves, microwaves, visible light is electromagnetic wave, all the way up to X-rays and gamma rays. And when you change the height of one of those waves, stretching or compressing it, you're changing intensity, but you don't hear those waves. Like X-rays, you don't hear X-rays. What happens with an X-ray, if you increase the amplitude of it, it becomes a more powerful X-ray. So maybe it could, I don't know exactly, more radiation. It's a stronger signal. Same thing with like a radio wave. Okay? When you increase or decrease a radio wave, we don't hear radio waves. I mean, your car or radio can pick them up, but our ears don't directly hear a radio wave. So by increasing or decreasing the amplitude of a radio wave, it would be a stronger signal. Maybe it could travel further than a weaker signal. Okay, so any questions on that one? All right, so that's a cosine with a stretch. Let's try a sine with a 1/2 of time. Okay, so before we even graph it, anyone tell me if this was a sound wave, how that would compare to sine x? What would the difference be? Sam? Yeah, this would be a quieter wave. It's going to compress it. It's going to be softer. If it was an electromagnetic wave, it would be a weaker wave, a weaker signal. All right, so let's make our table. So Sam, what column stays the same here?
The x.
Yep, can you tell me what my x's are?
Pi over 2. Pi. 2 pi over 2.
2. Yep, and one more?
Oh, 0.
0. Yep, first one's 0. Okay, now my y values for sine, I'm going to take all the originals and multiply them by a half. So half of 0, half of 1, half of 0, half of -1, half of 0. And that's it. That's your table. Now we'll make our sketch. Because I'm scaling my y-axis again, this is going to look exactly the same as every sine wave you've drawn so far. So we've got 0, 0. And you know what? Probably a better idea to put your labels a little bit lower so you don't draw through them at least as much. So pi over 2, we're at a half. Pi, I'm at 0. Still going to end up drawing through it a little bit. 3 pi over 2, about -1/2. And then 2 pi back to 0. Okay. Does anybody remember what this point is called? We talked about it yesterday in reference to a cosine function, but sine functions have them too. Something special happens at that point. I mean, it's an x-intercept, but something about the graph itself.
Point of inflection.
Yeah, it's a point of inflection. It's where the graph goes from concave down and then switching curvature to concave up. So right there is where the curvature switches. Okay. Any questions on that? Let's look at this one. What's going to be the amplitude of that graph when we sketch it? Yeah.
1.
1. So technically this is not an amplitude change, but what number is really in front of the cosine x in this case? Megan? Right, there's a number in front. So technically you are multiplying by a number in front. That's why it fits the pattern of an amplitude change. It's just the number doesn't change the amplitude. Okay, it's just going to flip the graph. Okay, so we've got our x's. And now the y values, you're going to take and multiply them all by -1. So Caleb, can you tell me what the y values would be?
So 0.
For cosine?
Oh, you mean the originals?
Final answer. Yep.
Oh, okay. For cosine, it'd be -1, 0, 1, 0, -1.
So normally when we sketch cosine, we get that more of the V shape. This time we're going to flip it over. We're going to get more of an N shape. We're going to get the up part of the wave. All right. So y-axis, I don't need to label it because I'm going to go by ones. X-axis, definitely need to label it. And let's see if I can move those down. All right, so we've got 0, -1, 0, 1, 0, and -1. And here's our graph. And remember, we continue on, but we're only sketching one. What's that called, what we just sketched? One. Big deal?
Period.
Period. One period, or another name for it is one cycle. Yep. So this is sketching the cycle that has the low, hits the middle, the highest, the middle, back to the low. And then it would repeat. Okay, so any question on that one? Okay, so that's our vertical stretch. And the last stretch we're going to look at is the horizontal stretch. So for trig functions, they give the horizontal transformations different names. They don't call it a horizontal shift, they call it a phase shift. They don't call it a horizontal stretch, they call it a period change. But it's the same idea. Okay. What's the normal period for sine and cosine? If you don't mess around with it, you just graph the basic function. What's the normal period?
2 pi.
2 pi. So what that means is, if that's 2 pi, and we're sketching part of a sine wave, that's what sine would look like if you don't change the period. Well, now what we're going to do is take something like that, and instead of having it have to go all the way to 2 pi, maybe we'll compress it by half as much. It only has to go to pi, or even a quarter pi, or something very small. Okay? So we can take the period and compress it, or we can take the period and instead of having to go to 2 pi, maybe it has to go all the way to 4 pi to do one cycle. Okay? So that's what we're looking at, stretching and compressing horizontally. Since it's a stretch, the operation involved in the equation is multiplication. But this time the multiplication is not in front, it's inside. All the stuff inside the parentheses, that's your horizontal stuff. And again, I labeled it with the letter B because now you should have a complete list of which transformations to do in which order. Phase shift, period change, vertical shift, vertical stretch, vertical shift. Those are the last two. And of course, if you have a problem where you say you don't have all four in the same problem, you just do whichever ones you have in the order I just said. We're going to be looking at examples where B is greater than 0. We could do less than 0. It would just cause a reflection. That would be a reflection that's a horizontal, which would be over the y-axis. But for our purposes, we'll just let B be positive. Okay, so period change, stretching and compressing the graph along the x-axis. So we know B is going to be greater than 0. Okay, B is never going to be negative. But does anyone think they could tell me when the graph would compress and when the graph would stretch? Depends on the value for B. I think they could tell me when the graph would compress and when it would stretch. Sean?
Stretch when it's less than 1 but greater than 0, and then shrink when it's like greater than 1.
And compress when it's greater than 1. Yeah, it's the opposite of what you would expect. You might think, oh, a bigger number stretches it bigger. Nope, not with the horizontal, it's the reverse. The bigger the number for B, the smaller, more compressed it gets. Okay, and we're assuming what Shauna said, B is less than 1, but it's also implied it's greater than 0. Okay, we're not going negative. Okay, so if I were to graph sine of x and sine of 3x, what's going to happen with the 3x is it's going to be compressed by a factor of 3. You could also say stretched by a third, because if you stretch something by a fraction, it really compresses it. So, for every one cycle of sine, you're going to get 3 cycles of the red one. Okay, you'll see it. If you focus on the origin from that point forward, it'll be very easy. There's 1, 2, 3. Okay, so you've got 1, 2, 3. 3 cycles of the red one for every 1 cycle of the blue one. Okay. Any questions on that? All right, so let's take a look at what that would sound like. So stretching and compressing vertically change the volume. What do you think stretching and compressing horizontally does? Okay, Megan?
Changes the frequency.
Yeah, it changes the frequency, and how would we hear that? What does that mean? Yeah, it's going to change the pitch. It's going to be a higher pitch or lower pitch sound. So the sound, kind of the default one I've been playing for you is 1,000 hertz, just to kind of model it. Okay, so there's 1,000 hertz. In terms of the scheme of pitch of a sound, what we can hear with our ears, that's not very high pitch. Does anybody know how high we can hear? Anyone have a guess at what the highest frequency is we could hear? Jane? You get a guess? Name a number and I'll play it. Unless it's too high, then I can't play it.
5,000.
5,000. All right. So let's put it on 5,000. And I want to play the same sound out of each speaker. Okay if I just get close to 5,000? All right. So we'll try 5,050 hertz. Okay, so let's see if we can still hear that. All right, so we can definitely hear it, and we can go higher than that. Let's try about 10,000. Okay, so it's 10,001 hertz. So definitely higher pitch, but we can still hear it. Anybody that couldn't hear that? No? All right. Let me getting a little distortion. Let me see if I turn the volume up there. Turn that one down a little. That sounds better. All right. So we got 10,000. Let's try. Let's go up to 13,000. Pretty close. Okay, so still higher pitch. Anybody that couldn't hear the 13,000? You can still hear it. All right, let's go up to, so compressed you can't even see the picture. It's just, don't even look at the picture. So let's try 15,000, or close enough to it. Okay, and still, anyone that couldn't hear that one? 50. All right, let's go up. Let's go all the way to, let's try 19,000. So at 19,000, I definitely don't hear that one anymore. As it gets higher and higher pitch, usually as you get older, you just can't hear the higher frequencies that well. So anyone that couldn't hear that, not the buzzing of the speaker, but it should be an extremely high sound. You couldn't hear it, Leo? No. I mean, I hear something. I hear like the static sound, but that's not the sound. That's my speaker freaking out. All right, so the highest frequency that generally we can hear is about 20,000 hertz if you had perfect hearing. And from the moment you're born, you start losing hearing. So eventually, as you get older, I've had some teachers like in their 60s, they can't hear even like 12,000 just because they just can't hear anymore. But so it depends a lot, not on your age, but also depends on what you do for a job and the kind of noises you're exposed to. If you work at an airport, taxiing airplanes and you're near jet engines all the time, you're probably going to have worse hearing than somebody who works stuffing bunny rabbits in a quiet room. So it depends what you do. Now, on the opposite end, we can go with a lower pitch sound. And with lower pitch sounds, you start to feel them. Like, I don't know if you really felt that high-pitched sound. You hear it, but it doesn't really vibrate the room. Also, because it doesn't travel well through walls, when I play that sound, nobody next door probably heard it. When I start to play the lower pitch sounds, they'll definitely hear it. So, it's low, but nowhere near what we could really do. So let's go a little lower. So now we're getting even lower to the point where now you're not hearing it out of the sound bar. Now you're hearing it out of a different speaker that's designed specifically for low frequency. I mean, in theory, you can go all the way down to 0. I can't generate sounds that low. 45 is about the lowest that my equipment can do. And listen to that one. So that's 45 hertz. Very, very low pitch sound. Travels very well through walls. And another interesting thing is, like, if I play that, I'm not turning down. There's nothing else in the room that really vibrated. All you heard was that sound, because there's nothing else in this room that resonates at 46 hertz. But as I start to raise the frequency, you'll start to hear different things will vibrate in different parts of the room, which is kind of interesting. So let me play that. So I don't know if you heard the vents over there started vibrating a little bit. So apparently they vibrate right around 57 hertz. So that's the effect of changing the frequency. And then what gets really kind of interesting is when you start playing two different frequencies at the same time. So let's put it right around there. Turn it down a little. So that's 481 hertz, more palatable sound. And let me play 480 and 481 at the same time. So it's hard to see from the picture, but the waves are a little off. And now you're getting this kind of, like, it almost sounds like the volume's going up and down, but it's like a pulsating. And the further apart the two waves get, the faster the pulsing is going to be. And now you can start to see it more on the right side if the two waves are off. That idea of playing two frequencies at the same time, that's basically how a phone works. So if you play, I don't remember the frequencies off the top of my head, but I think, let me try one real quick. 440 and 380. Not quite. What? Let me look it up. So all the buttons on your phone are generated by different frequencies. And for example, if you wanted to generate the number 1 on your phone, it's a 1209 hertz combined with a 697. Now, either one of those by themselves isn't going to sound like the button you're used to hearing. So if I play 1209, let's see if I can, is that going to work? Yep. 1209. And let me play another, I'll play the same frequency out of both speakers. That doesn't really sound like a button on the phone at all. But combine a 1209 with a 697, and it's going to sound exactly like you're pressing a button on the phone. So that's the button 1. So by generating the right frequencies on a speaker, I could actually dial a phone without pressing the buttons. That's something maybe if I have more time, or maybe sometime when we have a little extra time, I'll show you the phone thing. So just remind me to show you the cell phone thing, or any phone. The ringing, when you hear a phone ring, That's two frequencies as well. I think it's, I can't remember them. I think it was 340 and 380. That's not right, but not quite. 440 and 480. I'd have to look it up and find it again. But the sound of a phone ringing, the dial tone, and the busy signal, those are all just two frequencies, dual frequencies, played at the same time. There's some other frequencies over here, A, B, C, D. We don't have those on phones. I think there was some military use for those. They had special phones that had these buttons on them, but we don't have those. If I click it, let me just see what it says. I guess I can't click it. Also, the picture of what you just heard, the 1209 and the 697, played at the same time, looks like that. So that's the combination of two sine waves at the same time. Definitely a pattern to it, but it's not, and it's connected, but it's not a nice wave. Okay? That's what gives a button on the phone the characteristic of a button on the phone, that different kind of pattern. Okay, so any questions on that? Okay, so that's your phase shift. All right, so one thing that I'm going to ask you about with these kinds of problems, before we even graph it, is what is the period? Okay, so normally it would be 2 pi, but we're going to stretch or compress it. So the formula to find the period is 2 pi divided by b. Period is not b. B is the denominator of the formula to find the period, but it's 2 pi over b. Okay, so let's look at some problems where we calculate the period. Okay, so the first one is sine 2x. What's going to be the period of sine 2x? Okay, pi. It's going to be 2 pi over 2, which is pi. So what that means is the graph is going to have to go from 0 to pi to do its full cycle. It doesn't have to go all the way to 2 pi anymore. You've compressed this by a factor of 2. All right, cosine 1/3 x. Okay, what would be the period there? Yeah, 6 pi. 6 pi. Right? 2 pi divided by 1/3 gives you 6 pi. Which makes sense because we said if you put a fraction in front between 0 and 1, that's going to lengthen the function. So now, for this function to do its full cycle, it has to go 3 times as far as it normally would, all the way to 6 pi. Okay, how about here? What's the period of sine pi x? Yep, Rebecca? 2. So this would actually be a very nice one to graph because you could label your tick marks 0, 1, 2 on the x-axis. And from 0 to 2, it's going to do a full cycle. All right, let's look at this one. What's the period of 2 sine 3x plus 2? Leo? 2 pi over 3. There's some other numbers there that are affecting the amplitude and a vertical shift, but that has nothing to do with the period. Okay. Any questions on that? I want to look at what the range would be of this function. What does sine normally go between if you don't change anything about it? Sam? Yeah, it's normally -1 to 1, but we've doubled the amplitude. So if you double the amplitude, Now it would be between what and what? Yep. Yep. And we go from -2 to 2. But you've also done one more thing. You shifted everything up 2 units. So if you shift that interval up 2 units, what would the y values be between? Yep.
0 and 4.
0 and 4. So I might ask you a question on the test. What is the range of that function? It's going to have 0 as a low value, 4 as a high value. All right, so to figure out where the 5 points are going to go for a period change, well, we're stretching and compressing along which axis? Which axis are we changing? Yeah. We're changing the y's? We're changing the x's, right? Because if we stretch or compress the frequency, which is what we were just doing, it's stretching and compressing horizontally. So that means the y's are going to stay the same, which unfortunately the y values are the easy ones. So this time we have to work with the x column. If you're wondering what that little W is, that's an omega. And when I use a different book, that's the letter they use, but I think it makes more sense. It helps you to remember the order if you remember B instead of a Greek letter for this problem. Okay, so now to find the new x values, take the old ones and divide them by B. Or sometimes an easier way to think about it is multiply. What could I multiply by? If I could divide by B, that would be the same as multiplying by
1 over b.
1 over B. So it depends on the problem, because we want to avoid fractions over fractions. I mean, we still have to simplify, but at least if we can avoid that, that's good. So take the original x's and divide by B. Or think about it as multiplying by the reciprocal. Okay, this is a problem where you definitely want to think about it as multiplying by the reciprocal. Because if you don't, you're going to get fractions over fractions. Okay, so this is a period change. Dylan, can you tell me how we know this is a period change and not a phase shift or a vertical shift or an amplitude change?
Because the 1/2's inside the parentheses multiplied by x.
Exactly. It's inside the parentheses multiplication. So what you want to look for, inside, outside. Inside, it's horizontal. Outside, vertical. Next thing to look for, is it an addition or subtraction? Same idea. Or is it a multiplication? Multiplication is always a stretch. Addition, subtraction, always a shift. Okay. So we know it's a period change. Period change, y's stay the same. And now my original x's, 0, pi over 2, pi, 3 pi over 2, 2 pi. What am I going to do to all those x values? Yeah.
Multiply by 2.
We're going to multiply by 2. Okay, you've got to be careful that you don't mix it up. You can either divide by 1/2 or multiply by 2. But don't mix the two ideas. Right? Don't say like multiply by 1/2. Okay, so let's multiply everything by 2. So Shauna, 0 times 2? 0. Tessa, pi over 2 times 2? Pi. Pi times 2 is 2 pi. Juliet, 3 pi over 2 times 2? 3 pi. And 2 pi times 2? 4 pi. So we get a nice pattern. 0, 1, 2, 3, 4. Okay. Any question on the table? So we got our table. Now label the axes. Is there any axis here that it would be okay if I didn't label it? Because if you don't label, you're going to go by ones. So I'm asking, is there any axis here where going by ones makes sense?
One.
Yeah, I'd say going by ones on the y-axis is perfect. Definitely label these. And now plot your points. 0, 0, pi 1, 0, negative 1, back to 0. Okay. Any questions on that? So did this graph stretch or compress versus the original? Stretched, yeah. It stretched out by a factor of 2. It doubled the length. Okay. Normally, the sine function would have done a full cycle from 0 to 2 pi. Now from 0 to 2 pi, it's only doing half a cycle. All right, let's try cosine 2x. All right, Abby, how would I start this off?
You put in the values for y.
What's that?
You put in the values for y.
Yep, put in the values for y. And what are my y values going to be?
0, 1, 0, negative 4, 0.
Okay. Any thoughts on y values?
That's right.
1, 0, negative 1, 0, 1.
Yeah, what are those y values?
Sine.
That's for sine. So if you did that, maybe we could still get the x's right, because the x's for sine and cosine start off the same. So as long as you do the arithmetic correctly, but we would get the x's, we would get the y's wrong, and then that would make the graph wrong as well. Okay, just make sure we get the right y values. Okay, now I'm going to take all my original x values, and what am I going to do to them this time? Yeah. Yeah, I'm going to divide them by 2 or multiply them by a half. So you might notice the first one is always 0. If you take 0 and you double it, you take 0 and multiply it by a third, it's still 0. The only time that could change, actually you tell me, what transformation would you have to have done before this one that would cause the first number to not be a 0? Leo?
Phase shift.
Exactly, a phase shift. If you do a phase shift, because that's the first thing you do, that would cause the first number to not be a 0. Assuming you do a phase shift by something other than 0, obviously. Okay. All right, so we're multiplying everything by a half. So we've got 0. The next one would normally be pi over 2, but now it's pi over 4. Now I see the gap. The gap is pi over 4 each time. So the next one is plus pi over 4. So 2 pi over 4. Which is pi over 2. The next one is plus another pi over 4 because we got to keep the gap consistent. So we got 0 pi over 4, 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4. Okay, so there's my table. Right, this time the graph compressed. Normally it would go to 2 pi, now it has to only go to pi to do a cycle. Okay, so label your axes. If you don't reduce it, you wouldn't lose points, but generally we always reduce a fraction as much as we can. Alright, so we've got 1, 0, negative 1, 0, back to 1. And there's our graph of cosine. So in terms of a sound wave, because we compressed it, what kind of sound would that be? Sam?
Higher.
Yep, it would be a higher pitch sound. In terms of an electromagnetic wave, I didn't really talk about that, but what happens when you stretch or compress an electromagnetic wave is it changes the type. Radio waves have very long wavelengths. Wavelength is the distance from like peak to peak. When you start going up in the spectrum, like you get into X-rays and gamma rays, the wavelength is extremely short. It's very compressed. That's why it can penetrate through objects easier. Okay? Radio waves don't really work underground. Try to bring a radio underground, it's not going to work. But shorter wavelengths will penetrate ground. X-rays can go through ground a little bit. Gamma rays definitely can. Lead would stop X-rays because that's dense enough, but lead wouldn't stop gamma rays. So that's the problem. There isn't really a good way to stop gamma rays. So if you get hit by a gamma ray, it's going to go right through you. And obviously, we know what happens if you're exposed to X-rays too much. Bad things happen. Well, gamma rays would be worse. Okay? There's really no way to stop. All right. Okay, let's look at this one. So at first, when you look at it, it looks like it might be a pretty awful number to deal with in front of the x. But this is actually going to be the nicest graph we've done all week in terms of numbers. Okay, so we just did a cosine, so we already know the y values. X values. How am I going to get my new x values? Take the old x's and do what to them? Okay. We're going to multiply them by 3 over pi. Well, the first one was 0, that's still 0. What's pi over 2 times 3 over pi? Yeah.
3 halves.
3 halves, or 1.5. Well, now you know the gap between x values. Just keep that gap consistent all the way down. So what would my next x value be? Rebecca?
3.
Yeah, 3, 4.5, 6. If you don't want to do it that way, then just take all the old values and multiply them by 3 over pi, but that's what's going to happen. And as I just said, that's the nicest table we've had all week. Okay, there's no pi in it, so you could actually just label everything with 1s if you wanted this time. So I'm going to put the labels in just to put them in, but again, you don't need to because we're going by 1s. Okay, so we've got 0, 1. And 1.5, that's not an awful number because it's split right in the middle. So it's not an awful decimal to work with. 3, negative 1. 4.5, we're back at 0. And 6, 1. Again, looks the same as all the other functions we've done because I changed the scale. Right. Any questions on that? All right, so tomorrow we're going to start to look at the multiple transformations, okay, combining them in the same problem. We'll look at a few other properties of sine and cosine, and we'll also start solving equations like that. For now, we're going to solve it on the calculator by graphing it and finding an intersect. So you could probably do a problem like that right now. But eventually, the goal is to solve it without the calculator, okay, with algebra. Thursday, we'll finish up with all the other trig functions. We're not going to go into as much depth with them, but I do want you to know what they look like. Okay, so homework tonight is 8 questions. Same deal as last night. It's already on a worksheet for you. But if you lose it and you need to copy some problems, they'll be in the video.